This example is going to allow us to tie in the idea of a matrix representation for a system of differential equations with what a solution is going to look like, the type of which we're going to generate as we work through this material. The matrix equation is x prime equals 2, 1, negative 1, 0 times x. And I'll say for the duration, unless I say otherwise, when I'm reading a matrix, like 2, 1, negative 1, 0, I'm going to read this as rows. The solution is x equals the column 1, 3 times e to the t plus the column 4, negative 4 t e to the t. And we're to take that solution and plug it into the equation. And we could write the solution as x equals e to the t plus 4t to the t, and y equals 3e to the t minus 4t to the t. That's what the matrix representation represents. But we're going to do this using the matrices themselves. We first need x prime. So we'll compute that. X prime is equal to, now when we see the column 1, 3 times e to the t, those are constants, 1 and 3. And to differentiate the exponential, it looks like it doesn't change, right? E to the t. For the second term, we've got the column of constants 4 and negative 4. But then we have as the variable expression, so I'll write that, t e to the t. Well, that's a product of two functions, and so to differentiate that, we should use the product rule. And that derivative is going to be e to the t plus t to the t using the product rule. That gives us the column 1, 3 times e to the t plus the column 4, negative 4 e to the t. How about doing it this way? Plus the column 4, negative 4 times t to the t, right? We're just effectively distributing. We actually have like terms that we can collect. And to collect those like terms, we can add together the vectors that are being multiplied by e to the t. And so we have 1 plus 4 as the first entry, and then 3 minus 4 as the second entry, to give us 5, negative 1 e to the t. And then we have our 4, negative 4 times t to the t. This is our x prime. It's the left-hand side of the system that we're looking at. The right-hand side is that 2, 1, negative 1, 0 times x. We could distribute the coefficient matrix to these two vectors on the right that represent the solution, but I'm not going to do that. 2, 1, negative 1, 0. And then for x, I'm going to use the forms that we had when we wrote down the two equations, x and y, that were the solutions. So we have this 2, 1, negative 1, 0 times e to the t plus 4t to the t. That's the top entry. And then 3e to the t minus 4t to the t. Notice that what we have in what I just wrote down is a column vector. So when we multiply the two matrices together, or the matrix times the vector, we're going to multiply 2 by the top entry and then 1 by the bottom entry and add them together to get the first entry in the matrix on the right. That's going to look like 2e to the t plus 8t to the t plus 3e to the t minus 4t to the t. Then we're going to multiply negative 1 by the top entry of the column vector, and then technically 0 by the bottom entry of the column vector. And that's just going to give us negative e to the t minus 4t to the t. Collecting like terms, we can see that that's going to be 2e to the t plus 3e to the t, which is 5e to the t, plus 8te to the t minus 4te to the t is plus 4te to the t. And then that bottom entry doesn't change at all. And for comparison purposes, I'm going to write this as the column vector 5, negative 1 times e to the t plus the column vector 4, negative 4 times t to the t. Say that that's equal to 2, 1, negative 1, 0 times x, and point out that that's exactly what we got for the left-hand side x prime, thereby showing that this is actually a solution to the system.